Good afternoon to everybody. I'll now share my screen and start off with the talk itself, because this is a very vast topic, and I'll really try to cover as much as I can in 1 hour. Now, many of you will recognize this photograph as one of a spectacular display of an aurora. It is a grand display of an aurora over Bharati, the second Indian Antarctic station. And this photograph was provided to me by Dr. Gopi Simala of Indian Institute of Geomagnetism. Now, these spectacular displays are actually a signature of the connection between geospace and the sun, and which creates space weather. You've already heard some talk on space weather and so on. And you realize that the Earth's magnetic field plays a critical role, a central role in space weather. So before I go on to geospace, I will talk first about the Earth's magnetic field. Now, the study of the Earth's magnetic field, the subject of geomagnetism, began a long time ago. I will go over the history because it's interesting. In ancient India as well as China and some other places, people were aware of this mineral called magnetite, which attracted iron. But not until people started shaping the magnetite in the form of direction finding devices, needles, that the details, some of the characteristics of this magnetic field started emerging, Earth's magnetic field. This was the beginning, really. So in 1088, Chinese scientist called Shen Kuo is supposed to have provided the first written account of a suspended magnetic compass, which could be used for navigation. And he also realized that this needle did not really point towards the geographic north, and it pointed a slightly different direction. So he introduced the concept of the angle between the geographic north and the direction of the needle, called declination. So the Earth's magnetic field, any magnetic field is basically a field of force which acts on moving charges. A charge which is moving in a magnetic field experiences a force that is perpendicular to both the direction of the magnetic field as well as the direction of motion. Now, the Earth's magnetic field at some location in the northern hemisphere, Earth's magnetic field is basically a vector, so it has a direction as well as magnitude. So it points downward in general. And so there is an angle I called inclination between the horizontal plane, the surface of the Earth, and the magnetic field. And also this horizontal component of this field, as I've already mentioned, makes an angle with the geographic meridian plane, the northern geographic north, which is called the declination D. And so, if you want to really measure the magnetic field, you have to measure 3 components because it's a vector. And very often H, D, and Z are measured. If you have H and Z, it is easy to calculate the inclination I. Now, it's interesting that, with a needle, magnetized needle resting on a horizontal pivot, Robert Norman made the first determination of the dip angle at, this was in England, I think. And then William Gilbert, who was actually a trained physician, he constructed a sphere of magnetite and started experimenting with little compasses. And he came to the conclusion that the Earth itself behaves like a magnet. And just by observing the small changes that the compass needle made during a day, George Graham was able to see that the declination not only changed from one day to another, but it also varied with time on the same day. It followed quite a regular pattern every day, except on a few days when the declination showed shorter period irregular variations, and these were often coincident with, displays of aurorae in the extreme north. So these observations, and these were also simultaneously observed at different locations. So these observations were attributed to magnetic storms by Alexander von Humboldt. And in fact, this magnetic storms, the term is still used, as you know. And in 1832, Gauss made the first absolute measurement of the strength of the Earth's magnetic field by, sort of rotating, giving a twist to a magnetic field suspended by a vertical fiber. And when that happens, the Earth's magnetic field tries to pull it back in the direction so that it aligns with the magnetic field. It overshoots and starts oscillating. And by measuring that frequency, you can determine the strength of the horizontal magnetic field at that point. Now, Gauss and von Humboldt realized that, if the Earth's magnetic field is changing from one place to another and also with time, it is necessary to make continuous observations at a number of locations around the globe. So von Humboldt actually managed to convince the British that, in their, this was when India had not achieved independence, that in all its colonies, they should try and set up magnetic observatories. So that is how the first geomagnetic observatory was set up in Madras in 1822 and functions till 1881. Simla Observatory was also started by them. It worked from 1841 to 45. And in 1841, the Maharaja Ram Verma of Travancore, he had so much curiosity about this Earth's magnetic field that he on his own commissioned a geomagnetic observatory in Trivandrum, which functioned until 1870. In 1841, also geomagnetic observations commenced at the Colaba Observatory, which were discontinued only in 1906, that too because electric tram cars came to Bombay then, so which would disturb the measurement of the Earth's magnetic field. So then the director at that time, an Indian by the name of Nanabhai Moose, he actually selected this location at Alibag, and continuous measurements were made at both these locations from 1904 to 1906 to see if, this could be a continuous, series. And since the variations were pretty similar, and the geomagnetic measurements were started in Alibag Observatory in 1904 and continue to this day. They're still continuing. So this is one of the very famous old observatories of the world. And throughout the world, the Colaba Alibag geomagnetic data series go globally acclaimed. You will realize as I talk from my talk why it is necessary to have very long series of observations, and why we're also measuring, short time variations nowadays at seconds interval. Now, at present, there are a number of ground-based geomagnetic observatories around the globe, which are not, of course, uniformly distributed, especially because oceans and all, there are very, except for some few islands, there are not many open observatories. And naturally, if you want to really have good information about the spatial variation of the magnetic field, then you need to have a better coverage, which can be provided by satellites. So once the satellite, we moved into the satellite era, several satellites have been launched. Currently, there is a constellation of 3 satellites called SWARM, which were launched by ESA in 2013, I think. And they are providing this kind of, you can see what fantastic coverage satellites can provide. These are orbits all in high inclination orbits. That means that, the inclination between the equatorial plane and the orbital plane of the satellite is very large. This is about 87 degrees for these satellites. So they are almost polar in their orbits, and you can see that they can provide this kind of coverage, which is very important. But you will also realize satellites keep moving. So they cannot give you a continuous record of magnetic field variations at a given location. That's why ground magnetic observatories continue to be very important. And Indian Institute of Geomagnetism itself runs a dozen magnetic observatories stretching from Gulmarg in the north to Tirunelveli in the south and Rajkot in the west to Silchar in the east. So, these have provided data where you can see how things vary, at least in the Indian region, how the geomagnetic field components vary over short and long terms. Now, first, before I go over to the actual data from these observatories, I will tell you a little bit about the instruments that are used today in geomagnetic observatories. Basically, two kinds of instruments are used to measure the geomagnetic field in observatories. One which measures the absolute value of the geomagnetic field at an instant of time, and the proton precision magnetometers and overhouse magnetometers, which are basically quantum magnetometers, they are used today in place of earlier all magnetic needle-based instruments were used. So these are now used for making the absolute value measurements and to record the variations. Because the variations are over short time scales. Naturally, the variations can be as small as a few nanoteslas. Nanotesla is a unit that is used for measuring the geomagnetic field. It is related to, it is 10 to the power minus 9 Tesla, and Tesla is nowadays the unit that is used. So the other one, which records continuously the relative variations in a component of the geomagnetic field, those are called flux gate magnetometers. They are based on the concept of magnetic induction. So how does the proton precision magnetometer work? Basically, these make use of the fact that protons and electrons have quantum properties of spin and magnetic moment. Now, if you take a bottle full of some proton-rich liquids, such as kerosene or even water, so hydrogen-rich liquid as a sample, and normally there'll be these magnetic moments are either aligned along the magnetic field that is present or opposite to the magnetic field that is present, and these are these two populations may more or less equal, so the net magnetic moment will be very, very small. But if by closing the switch here and applying a current of a fraction of an ampere, I think, you can produce very strong magnetic fields, which will be directed along this direction. And that magnetic field will tend to align the magnetic moments more in this. There will be more, so there will be a net magnetization in this direction. And usually, the way this is done is that, whatever field that you're trying to measure, this field is kept at right angles to this, so that the magnetization is at right angles. And once you open the switch, the magnetization is free to rotate around the ambient magnetic field. And if it is at right angles, then the maximum amount of force is exerted by the ambient magnetic field on this magnetization. That is why, but the direction is not very important in proton precision magnetometers. That is why it makes it a very useful magnetometer if you want to carry from one place to another for measuring the absolute value of the magnetic field. Now, so from that precision frequency, which depends on the strength of the ambient magnetic field, you can calculate the magnetic field, because the gyromagnetic constant, which is a function of the proton mass, charge, so on, so that is well known. So by measuring the frequency of this, what is done is the signal is magnified, and then zero crossings of the signal are measured, so that you get the frequency of the of gyration of the signal, the precision of the magnetic moment of the polarized protons, and that net magnetic moment then persists with this frequency around the ambient magnetic field, and that frequency depends on the strength of the magnetic field, and you can then calculate the strength of the magnetic field. The other one, which is a flux gate magnetometer, that is, normally, I mean, there may be other types of cores also, but, you can have a ring core of an alloy with high magnetic permeability. As you know that, permeability is the property which will determine how material gets magnetized. And, so if you have applied current to magnetize the core, then initially the magnetization will rise, and then, linearly, and then it will tend to saturate. As you reverse the magnetizing force, it will not follow the same path, but in the reverse direction also it saturates. And this is, of course, as you know, is called a hysteresis loop. The advantage of a high magnetic permeability material is that, this loop is very narrow and this is more vertical. So the idea is that suppose you have an external magnetic field in this direction. This is set up actually to measure an external magnetic field in this direction. That is why you can actually have 3 flux gate magnetometers mounted such that you can measure all 3 components. And this is the drive winding, which drives the current through this wire, which will give rise to a magnetic field. You will notice that in one half, the magnetic field which is induced has a component parallel to the ambient magnetic field, and the other half, the ambient magnetic field, is opposite to the induced magnetic field. So here you can see that, this is the driving current. This is how it varies, sorry. Then if there were no external field at all, then in each window, you will have equal and opposite magnetizations in these 2 halves, and they will, reverse also at the same time, come out of saturation at the same time and all. So at any given time, there will be no net change in flux through the sense winding. There is another wire which is wound up like this around the ring core, so that if there is any change of flux, current will be induced in the sense winding and you will be able to sense it. But if there is no net flux change through this winding, then of course, no current flows through this. But if there is an external magnetic field, naturally there is an asymmetry, because the part which is having an induced field opposite to the existing ambient electric field, that will come out of saturation earlier and the other will come out later, and therefore they will not cancel out totally, and you will have a net change in magnetic flux through this loop. In each cycle there will be 2 such changes, and which will be recorded as induced currents or voltage along this voltage drop along this winding. So by measuring this, this will be at twice the frequency of the original driving waveform. And by measuring this, you can measure the strength of the variations. So this is ideal for measuring variations. So often, you will be surrounding them with coils to cut out, cancel out a large part of the Earth's magnetic field, so that you can measure the variations, which may be tens of nanoteslas, or at most 100 nanoteslas during the day. Of course, during storms, it's a little larger, so you can do that. Now, what kind of variations do you see? Now, as I've already said, people have noticed with a compass that the Earth's magnetic field changes from one place to another. This is along the longitude of the Indian sector, and these are all Indian stations up to Gilmer. These are former Soviet Union stations where you will see that H component is reversed, and this is because there is the current flowing in the ionosphere. during magnetically quiet times when there are no magnetic storms or something, they have very nice pattern, in terms of loops. You may have already learned about it, which are called SQ currents. And near the dip equator, where the Earth's magnetic field is horizontal, there is an additional current sort of flows because this becomes very large, which is referred to as the electrojet current system. So at Tirunelveli, the present day, our magnetic observatory, it is in Tirunelveli, not Trivandrum observatory closed down. But this is how the magnetic field varies in the Indian longitude sector from one latitude to another. This is just a component of H, D, and Z variations are shown here. Now, that was, of course, how the magnetic field changes on a day in 24 hours, when there are no magnetic storms. So that is to do basically with the electric fields that are present and the conductivity. The ionospheric conductivity is large during daytime because the ionosphere itself is created by radiation, electromagnetic radiation from the sun, X-rays, and extreme ultraviolet, as you must have learned. And so once the sun sets, the conductivity really decreases, the currents are very small. So that's why you have this daytime rise in the current and fall and so on. But, if you were to take annual averages of all these measurements and plot them for a long time, so 1850 to 2000, beyond 2000, so 1848 to 2009, actually, this data goes, you can see that there is a very long period variation also of the magnetic field. So the magnetic field that you measure at an observatory consists of a main geomagnetic field, which is generated by a geodynamo operating in Earth's fluid outer core. I'll be talking later about this. Then there is the magnetic field produced by quiet time ionospheric currents, some of which I showed. Then during magnetic storms, there are currents flowing in the magnetosphere, which add to the magnetic field. And then, any current that varies external to the Earth, which is varying with time, is going to induce currents because within the Earth, because the Earth is not an insulator, it has some electrical conductivity. And this is very useful. Actually, induced currents are measured to study the conductivity structure of the interior of the Earth. But the point is, you are making these measurements. So how do you know what part comes from within the Earth, what part comes from ionosphere, and so on and so forth? So for that, you have to resort to mathematical models. Now, the thing is, in science, for natural phenomena, so you gather a lot of data. Why do you do that? Because you want to see the pattern. Is there a pattern to the data? Spatial pattern, pattern of variation with time. And if there is a spatial pattern, can we say something about its origin, how its origin, from where is it originating? Can we say something about how it is going to look, what it will be its magnitude at a place where you have not been able to make a measurement? Can you say that or not? So for that, mathematical models are always very useful. This is based on the Maxwell's equations, which tell you that in a region where there are no currents flowing, the magnetic field, which is a vector, can be written as a negative gradient of a scalar potential V. And the scalar potential, the Earth is a sphere. So the coordinates that are useful are the distance, the radial distance from the center of the Earth, which is R. Theta is the co-latitude, which is 90 degrees minus the latitude, geographic latitude. Phi is the longitude, okay? A is the mean radius of the Earth. Now, Gauss introduced this, spherical harmonic expansion of the scalar potential, which satisfies this equation. And the solution of this equation can be put in this mathematical form. Those who are mathematically minded will appreciate that this sort of tells you how things are going, how the geometric field is going to change with latitude, longitude, and distance. And you will notice one thing, that there are many terms in it. Okay, so what happens is when n is 1, you can have m as 0 or 1, and you can have g 1, 0, which will have no variation with longitude, because if m is 0 there. And there will be an h. There cannot be an h10 because there is no contribution when m is equal to 0, g11 and h11. These constitute basically the field of a magnetic dipole, as if a bar magnet was kept at the center of the Earth, but its axis not coinciding with the rotation axis of the Earth, but at an angle, which can also be determined from GN imaging. And so there are two parts to this field. One part is such that, as you go further and further away from the center of the Earth, it decreases, and the other part increases. So the one that goes further decreases as you go further and further away from the center of the Earth, A by R. That is due to sources on the surface of the Earth or within the Earth, and the other one is due to sources from which are outside the Earth. Okay. Now, also you will notice, because of the structure of these functions, which are called Legendre polynomials, and cos m phi sin m phi, that the higher the value of n and m, the more structured you will get. That is, they represent smaller structures. The dipole is a global feature, a global structure. Okay, so that is why this kind of representation is very useful to even visualize what a magnetic field, Earth's magnetic field really looks like. And all the data goes into finding these coefficients, CNM, HNM, QNM, SNM. And then you find that more than 95% of the Earth's magnetic field really comes from within the Earth. Okay, and the rest only from outside the Earth. And as I said, the dipole is the most important, at the surface of the Earth. It is by far the largest of the terms. And, as you go to the higher and higher terms, the contribution falls. But, locally, if you want to know what is happening, then you have to go to high values of N and M. Okay. And if, because of that R dependence, you can actually extrapolate to what the field will look like at the core mantle boundary. And there, the smaller features start becoming more important, because they do not decrease as fast, they increase faster than the dipole. So that is why, and the two have different scales. You can see the core mantle boundary scale is on the right side, and that on the surface of the Earth. So the point is that the dipole is the most important, even at the surface of the Earth, and definitely if you go further and further away from the Earth, then the Earth's magnetic field starts looking more and more like that of an dipole. But if you go down to the core mantle boundary, certainly, you will find it much more structured. And even on the surface of the Earth, I will show you how complex the Earth's magnetic field is. But before I do that, I will show you, that I was showing you from Alibag, Kulaba-Alibag data, how the three components of the magnetic field change. So a few other observatories which also have this long series of data, they have been combined to produce this spherical harmonic description of the geometric field. And then it is seen that the dipole moment, if you just consider the n equal to 1 terms and just calculate the dipole moment of that magnet, which is not oriented along the Earth's magnetic field but tilted, that center dipole moment has decreased with time. There's a convention of represented negatively, but actually, if you look at it, the magnitude of that has been decreasing with time. Okay, and also the point where this, dipole crosses the Earth's surface in the northern and southern hemisphere, that also has been changing. In the northern hemisphere, you can see how the geometric pole position has changed over the years. In fact, a very recent picture, in fact, this is the latest, these are called international geometric reference fields, which are prepared with data from all the magnetic observatories, now satellites. So you have a pretty accurate picture, and going to large values of H, so you can get better and better details. But you will notice, first of all, that the dip equator, where the Earth's magnetic field is horizontal, the dip angle is 0, that is quite different from the geographic equator, which is just a straight line here. So in South America, it really makes quite a large angle with the geographic equator. And in India, it's almost parallel. But there is a difference, of course, in, the dip equator is here and the southern part of India, whereas we know that we are away from the geographic equator. Okay. Now, also, if you look at the strength of the magnetic field on the surface of the Earth, this is the field which comes from within the Earth. This is only the representation of the magnetic field that comes from within the Earth, which has been obtained from all these observations from geometric observatories and satellites. That gives you this picture where you see that the lowest field intensity is observed in the South Atlantic region. This will also turn out to be the place where the magnetic field is changing most rapidly. Everywhere I'll try to give you also the websites from where you can get more information. Well, these pictures are from the British Geological Survey geomagnetism website, so you can go there and get more material on it. But if you actually want to know exactly where, see, these are models. They can only, for very local things, you need to go to very high values of N and M, as I said. So the best picture is provided if you actually carry out a magnetic survey, which scientists from Indian Institute of Geomagnetism did in early 1990s. And they, and not only early 1971, 1981 and 1991, they make these surveys to locate where the Earth's magnetic field is actually horizontal by actually taking instruments to see where the dip angle is 0. So there they found that how, the dip equator itself has changed its location so much over 10, 20 years. Now it's back quite close to its, Tirunelveli is just a little north, 0.08 degrees north of the dip equator now. And, recently there was a lot of stir because, as I showed, there is, when I talk about the geomagnetic pole, I'm only talking about the centered dipole. Just as I talk about the geomagnetic equator, it is just the equator for the dipole, but centered dipole, which is just be tilted to the equatorial, geographic equatorial plane. But if you actually have to make a measurement of where the dip equator is, you have to make measurements there. So likewise, if you want to measure where the north magnetic pole is, where the Earth's magnetic field will be exactly vertical, that point has changed over time. And in recent years, it has moved very fast. From 2000 to 2020, in the last 20 years, it's moved so much. And for the last 100 years, it moved that much. So there was a lot of questions really of what is making it change so rapidly, because, airfields everywhere have a way of marking their runways using magnetic coordinates. So, you need to know how the magnetic field changes, for navigation also. So as I said, these models, not only the International Geomagnetic Reference Field, it not only provides, for instance, the geomagnetic field that was there in 2020, but it also gives you the rate of change of the of the geomagnetic field. Okay, the secular variation and secular acceleration as well. So using those, you can extrapolate to, you can find out what the geomagnetic field is today in 2023. You can extrapolate to 2025. Usually these fields are revised every 5 years. So the secular variation, using that, you can see that between 2014 and 2020, the Earth's main magnetic field has changed a lot in the South Atlantic anomaly region, So a new low spot has emerged here. And so that is the thing, if you have to get down to a few 100-meter scale size, you have to go to very large values of n. So these mathematical models are very, very useful for that. Because once you have a mathematical model, then you can start building a theory also, which will also give you a mathematical model. You can compare the two. Okay. Now, how is this magnetic field generated? The part which comes from within the Earth, not the crustal field, because as I showed you, I think from n equal to 12, 13 onwards, the field is from magnetization in Earth's crust. It has nothing to do with the geodynamo operating in the fluid outer core of the Earth. But how do we know that the Earth's outer core is fluid and so on? That information comes from seismic wave propagation. Seismic waves are basically, which propagate within the Earth, are of two kinds. One is the P wave, which is a longitudinal wave in that the particles of the medium travel back and forth in the direction of the wave. So that there is, rarefaction, compression, and so on. Okay. And the other kind is shear wave, which involves particles of the medium moving transverse to the direction of wave propagation. In this case, once you displace a particle from its original position, there has to be a restoring force to bring it back. And for any wave motion, you always need a restoring force which tries to bring it back to the original position. It overshoots, and then again it tries to come back. That is how you get waves. But this shear wave, it cannot happen propagate in a liquid, because as you know, a liquid does not provide any resistance to a change in shape. So if you push it upward, you can keep on pushing it upwards. It will not even try to come. It will on its own not oppose that. So therefore, when you have an earthquake, say at this location, and that earthquake signals are measured around the globe, it was found that the S wave pattern, which travels slower than the P wave, so you can distinguish actually the seismologists can distinguish S wave and P wave. That there was a whole shadow region where S waves were not observed, and that led to the conjecture that the outer core must be fluid, that the seismic waves cannot enter there. The P waves do enter, but then they are refracted. Just as light is refracted when you enter a different medium, so do seismic waves and so on. And for that also there is a shadow zone. Now the thing is that by looking at the travel times of P waves and S waves of large number of earthquakes occurring in different locations and measurements at different, you can model the interior of the Earth, which is not changing so rapidly. So you can see that what kind of materials will be there, or what temperature and pressure. Basically, the speed of propagation of the seismic waves depends on elastic constants, and then you take these different materials and conduct experiments in the lab at high temperatures and pressures which are supposed to exist within the Earth, and then you realize that that the core is a liquid because of the high there is high temperature, but it's not ionized. It is just a liquid because of the high pressure. And further, in the inner core region, the temperature that is prevailing is lower than the melting point of iron. So, it's frozen iron, if you wish. So it's a solid inner core. So Earth has a solid inner core of dimension about 1,300 kilometers. And this outer core is present about 2,900 kilometers before the surface of the Earth. So there is a fluid outer core. And you know that the Earth is spinning around its rotation axis. Then Earth is hotter deep inside, so that can drive convection, okay, in this liquid. And then you can have compositional buoyancy also, in that it's not pure iron that flows in the outer core, but iron mixed with some lighter elements. So what happens with time, the iron tends to condense onto the inner core and the lighter element is released, which moves up and thereby inducing convection in the core. And then once if there's any magnetic field, any motion will give rise to currents because iron is a conducting fluid. So these currents in turn will generate a magnetic field, and the currents themselves will be also acted on by a force by the existing magnetic field. So anyway, so the whole thing is quite complex. You have non-linearities because there's a feedback because of this force exerted by the existing magnetic field on any current that flows in the outer core. But altogether, you end up with a magnetic field which is as complex as what you've seen, which comes out from these measurements. So basically, the idea is it's a dynamo which operates because there is a conducting fluid which is moving around in a magnetic field. So an EMF is generated, and that gives rise to a current, which in turn generates a magnetic field. That's how the Earth's magnetic field is sustained. So that is the geodynamo. Now, we have seen, of course, that the Earth's magnetic field coming from the interior has a secular variation. It changes over time scales of, tens of years, hundreds of years, and thousands of years. But even on a longer time scale, there is information available about how the Earth's magnetic field is changed. And that comes from processes inside the Earth. You know about tectonic plates, which are sort of sliding over the mantle. And these tectonic plates, which lie beneath the oceans, they tend to pull apart at these mid-ocean ridges, and new crust is created by magma which rises up from the hot magma, which is molten rock which rises up from the mantle. And that, as it comes out and cools down, it acquires, when its temperature falls below the Curie temperature, it locks in the magnetic field. It's a magnetic material, so it locks in, it has some magnetic material. So that locks in the magnetic field which is present at the time, and then it slides over. So it's like a conveyor belt on both sides of the on the lithosphere. You'll see these stripes of magnetic field variations which show that magnetic field has reversed in the past. Earth's magnetic field has not always been directed as we see it today. The last reversal took place some 800,000 years ago. And, there are always conjectures about when the Earth's magnetic field is going to reverse again. Probably not in a few thousand years more, at least. But that is the thing, that information comes from the seafloor spreading. This phenomenon is called seafloor spreading. So you have magnetic field measurements by ships going across, and you will see these normal reverse. So that has given you the time scale for reversals also. Earth's magnetic field reverses in a very irregular manner, which is expected because it's a non-linear phenomenon. In fact, it's very surprising that the solar cycle still shows, an 11-year cycle for the sunspot and a 22-year cycle for the magnetic field of the sun. But, people have tried to actually do simulations of the geodynamo, and these have shown how the Earth's magnetic field reverses, and that the reversal is not like just a dipole flipping. It's not like that. The reversal itself, the process takes maybe a few thousand years, and during the reversal, the dipole field weakens, and so the multipole fields, other fields become very complex. So there's a very complex kind of field that will be there while the reversal is going on. And once it is reverse polarity, again, it will assume a character where it's mainly dipolar, not entirely. But in fact, in India, there is a group in Indian Institute of Science, Professor Vinod Srinivasan's group, which is doing the simulations of the Earth's magnetic field and looking into what causes the reversals. which is, you will realize, is a very important question. Okay, so now I come to geospace. Okay, the Earth's ionosphere and magnetosphere constitute the geosphere. The Earth's ionosphere, you've already learned, is produced basically by X-rays and ultraviolet radiation from the sun. The sun emits electromagnetic radiation over a vast spectrum. We, of course, see the light and heat. You know, those change very little, but over a solar cycle, very, very little. I mean, we don't even realize that there's any change. But X-rays and ultraviolet can be quite variable over a solar cycle. From minimum to maximum, there's a lot of variation. And because as you go down, the intensity of the solar radiation decreases, whereas we will see that the neutrals increase in number. Therefore, you get these layers. The F layer is the most dense and highly variable. The thermosphere, I think you've already learned that the neutral atmosphere has this structure based on temperature alone. There's the troposphere, stratosphere, mesosphere, and the thermosphere. The ionosphere is mostly, by the ionization of the thermosphere. And so, we will be concerned about what happens in the thermosphere. Now, the neutral atmosphere, as you know, is in hydrostatic equilibrium. What it means is that, the density is decreasing upwards. So there is a pressure gradient, which points downward. So there is a force, upward force due to the pressure gradient. And that is balanced by the downward force of gravity. And that tells you ultimately the density of neutrals is going to decrease exponentially high to the scale height, which depends on the mass of the molecule or atom. And therefore, the lightest atoms are going to be found at the highest in the highest reaches, and the molecules are found at lower heights. And the region where we are interested, atomic oxygen dominates. And therefore, when these are ionized, you get these layers with different composition. Once again, the F layer is mostly atomic oxygen ions. The E layer can be NO plus and so on. And the molecular ions dominate at lower latitude, lower heights. So this tells you, but I think this also you may have already learned about, how the D region, E region, F region, F. During daytime you have two F layer, F1 and F2, because the recombinations are different. The molecular ions recombine much more quickly than the atomic ions. So F1 layer, which is mostly NO plus ions, disappears at night after sunset, but F2 layer remains. And in the F2 layer, what happens is, you still have the thermosphere. One thing that you'll notice is that the number of neutrals is far greater than the number of ions or electrons, up to quite a high altitude. And that means that any collisions with neutrals will also be important. In fact, those compete with the gyration of these electrons and ions around the magnetic field. So magnetic field and neutral collisions, they compete with each other in controlling the dynamics of the ionosphere. The electrons, being lighter, gyrate around the magnetic field very, very rapidly. So, the electrons tend to be magnetized, as I said, whereas the ions, only in the F region, they are also, the neutrals are lesser. This is all logarithmic scale, so fewer collisions, the magnetic field dominates. So at lower heights, in E region, for instance, the neutrals collision of the ions with neutrals is important. You cannot ignore, because the gyration frequency, the rate at which the ions go around the magnetic field is not as high as that of electrons. Okay. So in the F region, what happens is electrons and ions move together, and because now both are controlled by the magnetic field, and they have this drift which is perpendicular to any electric field that exists and magnetic field that exists. The magnetic field northward and electric field in the out of the plane, the paper, you have an upward movement of the electric field. So then eastward electric field will give you northward, upward E cross B drift. And once they go up, gravity, pressure gradients, they will try to pull them down. Then there are also neutral winds, which if there is a wind which blows towards the equator in the southern hemisphere, it will tend to push it up the magnetic field lines. In the northern hemisphere, it will try to push down so there may be, the two ionization crests are not equal, but nevertheless, there is these equatorial ionization anomaly regions which are very important. Now, how do we know that there is this plasma distribution, large-scale plasma distribution in the ionosphere? What is the distribution? So for that, there are a number of instruments. One is the ionosonde, which a pulse of frequency varying from, say, less than 1 megahertz to 20 megahertz, fraction of a megahertz, 20 megahertz, it sweeps through that. And, depending on the frequency, it is reflected from a particular height, because what happens is these radio signals, they are electromagnetic signals, which are nothing but fluctuating electric and magnetic fields. Okay, the fluctuating magnetic field can be neglected because the Earth's magnetic field is much greater than the magnetic field of the signal. But the fluctuating electric field makes the electrons oscillate. The ions are much, much heavier, so they are assumed to be stationary. So there's a net polarization, and that sort of alters the electromagnetic wave speed. And so, the group velocity of high-frequency radio pulses is actually determined by the refractive index of the medium, which is given by this, where omega p is the plasma frequency. What is the plasma frequency? In a plasma consisting of electrons and ions, if you displace an electron from an ion, the ion being positively charged will try to pull the electron back towards it. Electron will overshoot, as I said, so it will have a wave motion. So these are called, basic plasma waves, and the frequency of this, intrinsic frequency of this is called the plasma frequency, which depends on the electron density. E is the charge, m is the mass of the electron. So you can see that depending on the density of the ionosphere at a particular point, the signal of a particular frequency will start to get to a point where the group velocity becomes zero practically. So the signal will take a long time to come. So here what is plotted is a virtual height. Why? Because this is calculated from the time it takes for the signal to return. After it's transmitted, gets reflected and returned. From that you can. But you assume you don't know what is the speed. So you assume that it's traveling with the velocity of light. Okay. So, and then you take. But if it is close to a point where the group velocity becomes very, very small, it's going to move very, very slowly, and it is going to take a long time to return. So the virtual height tends to become very large, as here. And that is where these are the critical frequencies which are related to the plasma frequency of the layers. But the problem is that we still have to get to the real height, which is done by going back to the equations, this is the refractive index. So wave is actually, the signal is propagating not with the velocity of light, but with a reduced speed that keeps on changing as you move up. So what is the real height? And then you can from the critical frequencies, you can say how the electron density varies with height, but only up to the maximum. Because beyond that, what happens is once you increase the frequency beyond that, it will just go, go past the ionosphere peak. It will go beyond that. It will not get reflected, and that's what happens. That is how we can get the GPS signals transmitted from satellites, because these are at gigahertz frequencies, which is much larger than the plasma frequency. Peak plasma frequency maybe somewhere in the neighborhood of, even if you say 20 megahertz. So these are much less. So these just go through, so they can come to your receiver. Now, Indian Regional Navigation Satellite System has its own satellites in geostationary orbits and geosynchronous. You know that both geostationary and geosynchronous orbits have 24-hour periods. The difference is that geostationary orbits are in the equatorial plane. So if a satellite is there in the equatorial plane, orbiting at 24 hours with a period of 20, you are going to see it will be stationary to an observer on the surface of the Earth. So, that's why they call geostationary. Whereas if the orbit is inclined to the equatorial plane, it will come back to, say, the point where it crossed the equator at the same time, But at other times, you will see it performing sort of a figure of 8. Now, for these global navigation satellite systems, Earth's ionosphere is a source of large errors in positioning. And but the boon for ionospheric physicists is that you can also get the total electron content along the signal path by using two different frequencies, as GPS does. It has an L1 frequency transmission and L2 frequency transmission, which is slightly different. Now, we have seen that the refractive index depends on the frequency and the density of them. Now, if you were to, the pseudo range, as you know, is the term pseudo range is used because it's not the true range. It has contributions for many things, and including the ionosphere, because it is traveling not at the speed of light, but at this multiplied by the speed of light, so somewhat less than speed, is delayed, and that sort of increases the range, because you're calculating range by just looking at the time taken by the signal to traverse from the satellite to their receiver. So since that range depends on the total integrated electron content along the signal path, if you have two different frequency measurements, you can actually calculate the total electron content. So this became a tool in the hands of ionospheric physicists. And now routinely these kinds of maps are produced of the vertical total electron content. The slant electron content is sort of based on certain assumptions, converted into vertical total electron content. And you can see the ionization anomaly that I was talking about. This region is the Indian region, basically. So you have the dip equator passing through the southern part of India, and you can see that northward of the dip equator, you have a peak in total electron content, and that is due to the ionization anomaly. And this is in the post-sunset hours. This is 1930 Indian Standard Time. Now, what happens is the ionosphere is not always very smooth, because the F region has maximum electron density, plasma density. So basically you have a higher density fluid resting on a lower density fluid as well. This is a basically unstable situation, in that if there is some perturbation here, it will tend to grow. And then as it grows, the low density region will move upwards and develop structure. And that is precisely what happens in the ionosphere. This is called equatorial ionosphere, where the Earth's magnetic field is horizontal. You need that horizontal magnetic field, because that is what prevents the heavier plasma from just coming down. Because as I said, electrons and ions cannot move easily across a magnetic field. They tend to go around the magnetic field. When they come close to a magnetic field, they will start gyrating around the magnetic field rather than go across it. So the Earth's magnetic field, of course, plays a critical role, and that's why the initiation of this phenomena called the plasma bubble, the low density region, is in the equatorial region. But this whole phenomena is such that it is, the plasma sticks to the magnetic field lines. So whole regions along the magnetic field are depleted and have structure, which are called irregularities, which scatter radio waves. And that ionosound, I was showing on a day without any irregularity, such clear signal. Now you can see that the nighttime ionogram from Tirunelveli is showing this spread in range of virtually. This is called range spread F. In fact, this is the first time that people came to realize that there are irregularities in the ionosphere which are doing that. And then, of course, radar came in and so on. And now we have GPS. And this is a picture of actually the GPS signal. You can get the total electron content, as I said. This is showing how there is a decrease in density due to a plasma bubble. And the signal, the intensity is fluctuating. This is actually not very strong scintillations. But this refractive index variation, which scatters ionospheric irregularities, as you can see, if delta, there's a variation delta n in the electron density, then the refractive index is going to vary. This will happen on different time scales, spatial scale sizes. And if there are inhomogeneities of scale sizes 300 to 400 meters, then they are able to scatter the GPS signals, GNSS signals, and they can give rise to very strong, this is the signal to noise ratio, very strong fluctuations in the signal strength, so that there are, the signal can fade at times. You can lose the signal that way. And, here, if you were to remove the large scale variation, you will see the phase also fluctuates, and the phase fluctuating very rapidly is equivalent to a shift in the phase, so that the lock of the GPS receiver, a GPS receiver basically locks onto a satellite as it becomes visible over the horizon. And that lock can be lost due to rapid changes in phase. So scintillations are a problem. If you are going to use GPS, GNSS for navigation, scintillations is something which is going to cause a lot of problems. And, there is a MST radar facility at Gadanki, and which operates at 53 megahertz. So normally what happens, electrons are always agitated thermally. So they are randomly moving around. So they do scatter radio waves, this random movement of the electrons. But that is a very weak signal. It's called an incoherent scatter signal. So there are very powerful incoherent scatter radars in the world which actually measure this, and that gives you a lot of information. But if you don't have such a powerful transmitter, then you can also, look at the signal which is coherently scattered when there is some plasma wave phenomena which sort of organizes the electron movement, electron ion movement, the plasma movement. And that happens when a plasma bubble, the irregularities evolve in a plasma bubble. This is scattering for radars. The backscattering is produced by irregularities of size half the wavelength of the operating frequency, the radar signal. And for 53 megahertz signal, basically this is coherent scattering by 2.8 meter irregularities. You can imagine the structure, starting from thousands of kilometers, you can have structures going down to a few meters and even centimeters. So these are, this is how variable the ionosphere can be. And from one day to another, you can see, the MST radar Gadanki has been very useful in studying the variability of these irregularities from one day to another. And they're continuing to be used, and there are fancier radars now. Now, the Earth does not, of course, live in isolation with its nice field, dipolar and all that, because it's connected to the sun. Sun's outer atmosphere is constantly expanding. So that is in the form of a solar wind, which impinges on the day side of the Earth's magnetic field, compresses it, and pushes back the field lines to long distances on the night side. Okay, so but apart from the solar wind, there are occasionally coronal mass ejections from regions of active regions of strong magnetic fields on the sun, which are also sources of solar flares. And this coronal mass ejection consists of billions of tons of plasma, which carry with it the solar magnetic field, which impinge, and then a lot of things happen. The Earth's magnetic field actually protects us from these highly energetic particles, not only from the sun, from other galaxies as well. And, so there is this nice cavity which is created by the magnetic field, which is called the magnetosphere, where the geomagnetic field dominates. And we need not worry that the sun will lose all its mass, because although it loses billions of tons of plasma in a coronal mass ejection, its weight is some 10 to the power 30 kilograms. So it will take billions of years to lose the mass. Now, as I said, the coronal mass ejecta, they carry with them the solar magnetic field, which is called the interplanetary magnetic field as it gets near the Earth. When this has a southward component and the northward component of the Earth, they reconnect. And this also you must have done. So some of the Earth's magnetic field line now open up, in that their other feed does not come back to the ground. They're pushed on the night side, and on the night side, they can sometimes come together, reconnect again. And then the magnetic energy is converted into kinetic energy of the plasma and is pushed towards the Earth. And that, gets trapped by the Earth's magnetic field. Some of them drift, in a protons drift westward, electrons drift eastward, giving rise to a westward current, which is called the ring current. And that is the signature of a magnetic storm. So this is once the magnetosphere is distorted, there have to be many currents which will produce magnetic fields to distort this, create this kind of a configuration for the magnetic field. This distortion is caused by many different current systems. One of these is the magnetopause current system, which is such that, that the inward of the magnetopause, the Earth's magnetic field is increased, the northward magnetic field is increased, and outside the magnetic field is cancelled. So this sort of forms a kind of boundary, if you wish. This is the ring current. And then there are also, because there are oppositely directed magnetic fields above and below, the below part is not shown, there must be a sheet of current which will give rise to this configuration of, earthward and away from Earth, configuration of parallel magnetic fields. And these currents also flows through these tail currents which flow in the magnetic tail region. And all these, then there are currents which field-aligned currents which flow in and out of the auroral ionosphere, because there is somewhere the current is not continuous, so it has to close, and that is how there are these field-aligned currents which you have very highly intensified currents in the auroral regions during magnetic storms, which also you must have learned, which actually produce effects even in the lower latitude ionosphere. Then there are the radiation belts. I think you may have learned about the radiation belts, and someone talked about the magnetic, which are very important because these trapped magnetic electrons and ions, they are further energized, and the actual mechanism for energization is still people are looking at it. But the point is that these highly energetic electrons in the outer radiation belt, and mostly protons in the inner radiation, they have different sources though. They are in regions where you have geosynchronous. These are not fixed distances; they change as also the ring current distance. So you can have geosynchronous orbits in these regions, and then these energetic particles can bombard the satellites, and that can create problems. Now, what do we see during solar transient event? Solar flare followed by coronal mass ejection. What do we see in ground magnetic observatories? You see that when the solar flare effect in magnetic field is caused mainly by changes in the electrical conductivity of the ionosphere. Electric fields may be different, but the solar flare electromagnetic radiation that travels at the speed of light. So that will reach, Earth's ionosphere very quickly, few minutes. So the solar flare effect you see at the time of the solar flare, almost in 8 minutes. And then, the next day turns out to be almost normal. All the things are happening because there is a coronal mass ejecta, which is on its way to the Earth. But those are particles which move much more slowly. They may be moving at a few hundred kilometers per second and so on. So, and they have a long distance to cover, 150 million kilometers. So they take their time, and when they finally arrive, they produce the magnetopause current, then they produce the ring current, and the ring current being westward, it produces a negative H incursion in all these different observatories in the Indian region. And the SIM-H index I have shown, which is an index calculated from many low latitude observatories. And that is supposed to be the sign of a magnetic storm. That is the intensification of a ring current. Here you can see that the ring current has intensified. And what has happened is, when the ring current intensifies, and there are two things happen. One is, normally the low latitude, equatorial and low latitude ionosphere is protected because you have closed field lines there. The open field lines, due to magnetic reconnection, you would notice are naturally at the higher latitudes. But what happens is that this shielding is partly disturbed because the currents, field line currents that flow into the high latitude ionosphere, they're imbalanced. So some of that spills over and spreads, creates electric fields in the low latitude region very promptly as soon as when that storm occurs. These promptly penetrated magnetic fields cause problems. Because sometimes if the ionization is pushed up, it takes longer to recombine. So you have higher plasma densities. And that is what is seen here at these three stations in the Indian region. From the GPS measurements, you derive the vertical total electron content, and then due to the storm, there is this enhancement. And since the GPS signals are affected by the electron density, you can see that the sudden increase in densities can create a problem in position measurement. Now, also, what happens to the signals depends also on what happens in the ionosphere during a storm. One of the things that I said is a promptly penetrating electric field can raise the height of the ionosphere. On this day, 17th March, for instance, the height of the ionosphere is way above what it was in neighboring days. And as a result, the plasma bubble, which grows more efficiently if you if the F layer is raised in height. And on this day, there were plasma bubbles and irregularities which produce scintillations on the signals coming from various GNSS satellites. And there is an index called the S4 index, which is used as a measure of the strength of ionospheric scintillations. It is nothing but the standard deviation of fluctuations of the normalized signal strength. And these circles are shown, for different strengths, and different sizes are also shown. So red and black are, fairly strong, moderate to strong scintillations. So you can see that in probably the anomaly region is also pushed higher. The very strong scintillations here would create a lot of problems if you want to use GNSS satellite signals to navigate. You want to use your airplanes, you want to use these signals to, for instance, for descending, during their descent. So it is still a problem in the regions like US, where the ionosphere is really not as turbulent, never becomes as turbulent as it does in the low latitude region because of this equatorial plasma bubble phenomena. But in our region, we have to be really careful about when we can use the GNSS signals, because if the signal is fluctuating so rapidly, one thing is, as I said, you can miss the signals. The phase is going to fluctuate. There can be loss of phase lock, so there can be cycle slips. You can get erroneous information, and your position information can be quite inaccurate. Okay, and for landing an aircraft, you need very good precision, particularly in the vertical direction. So therefore, ionospheric scintillations are something we have to be concerned about. This is a phenomenon of the geospace, particularly in the equatorial low latitude region where India is. So, Indian scientists have been doing a lot of work in this area. And now I will tell you about the largest geomagnetic storm event recorded ever. It was recorded in our Colaba Magnetic Observatory in September 23, 1859. It was so large that actually auroras associated with the storm were sighted even in Panama and all. Recently, I think in April, there was a news item that magnetic storm caused aurora to be sighted from Ladakh. The Indian Institute of Astrophysics has an observatory there. The thing is, with such a large magnetic storm, people are still trying to simulate what will happen in the ionosphere. Today's technology is so heavily dependent on various things, such as, satellite-based navigation is everywhere. So if that is affected, life can be severely affected by geomagnetic storm. That is why it is necessary to try and predict a geomagnetic, which is not an easy thing, because this whole magnetic reconnection, it involves many different things. The magnetosphere is a very complicated, complex region. And so this is basically the summary of my talk. And now I'll take questions.